Hello everyone, can you hear me? All right, all right. So we'll start in a couple of minutes. Let other people also log in. So we'll wait. All right. So, hello again. Am I clear enough? Should we start now? All right then. So, last session was sort of half session, and in the last session we discussed about streaming jobs. All right, discussed about streaming jobs, and so n- what do we want to do today is we want to understand those four problems which we gave in the session 2. All right. So to compute the frequencies of the letters, do you really need MapReduce? Yes. Yes, it can be done without MapReduce, definitely. But in your opinion, do you think we should do with MapReduce or without MapReduce? Depends on the volume of data also. That's right. That's right, Chandra. Depends on the size what we're talking. Since the data is in GB, I don't think we need an overhead of sharing merging step. That's correct. With MR will be better optimized results. That's correct. Can be done easily if you have access to programming language. Right, right. So that's correct, Sashi. All right. So yes, so you are correct. As a quick number, let me tell you something. So if you have 1 terabyte of data, reading from the disk would take around 5.8 hours. Even if you are reading the data continuously, reading 1 terabyte data from the disk takes around 5.8 hours. All right. So if your data is in TB and you want to compute the frequencies, you cannot, no matter how you do, using one computer, you cannot bring down the you cannot bring down the time less than 5.8 hours. Okay. Chandra says I don't have to worry about me coding around load balancing. That's correct. And with MapReduce, using map, MapReduce might increase the speed at which we get the results. Correct. That is correct. So when the data grows into the sizes of hundreds of GB or terabytes, probably MapReduce is a better approach. Otherwise, otherwise your normal computer would suffice. Okay. So as a good number, okay, I'll just going through some numbers. L2 cache, RAM, speed, disk. Alright. Know these numbers. These numbers are good. Alright. Basically, this diagram shows a nice thing. It shows you how fast are various things. Okay. And in this, the reading of 1 MB data from the disk, it shows that it takes around 20 milliseconds. Okay. So to read 1 MB data, it's 20 milliseconds. And to read 1 GB data, it will be close to uh, 20 seconds. Okay, it will be close to 20 seconds. And to read 1 TB, it will be 20,000 seconds, which is around 6 hours. Okay, and here you can see that if you have solid state hard drive, is 20 times faster than this one. The time taken by normal hard drive is 20 times that of SSD. Okay, so if you are having SSD, then lot of problems are solved. But most of the time these IOs will still be a bottleneck. But problem with SSD is they are quite costly for are of a smaller size. All right, just a second, it's coming too much of noise. Okay, so without MR approach, the strategy is straightforward. All you need to do is create an integer array of 26 size, scan one character at a time, and update the particular uh, element of an array, right? So, so this approach is clear to you, right? You create a big array of numbers, 26 numbers, and then keep on updating the corresponding index one at a time. All right. Sounds good to you? Am I coming through clearly? All right. Then now the problems with this approach are, you can actually tell it quickly so that I can move. So the approach is quite simple. You keep reading this text file from beginning till end, and for each character, you keep updating this array. If it's not alphabetic character, we just ignore it and move forward. IO load and CPU performance. Right. So here, CPU will not be too much of an issue. CPU will not be too much of an issue because CPU is not doing much. Okay. So CPUs will be fairly empty. The main time will go in reading from the disk, and disk will be the blocking operation. And in such scenarios, as Rohit says, that in such scenarios when there is a lot of disk and CPU is free, you can actually do a lot of parallelization. Okay. You form a queue, let reader from the disk keep on putting the data into the queue, while the processor who is computing the frequency will read from this queue and will compute the frequencies. All right. And the other thing which you should note is the memory will not be a bottleneck here. All right. So the next step is to create mapr around this approach. All right. Let's let's see how will MapReduce look like. The most common and simple approach is mapper1, not like this. Okay. So each mapper does this job. Okay. For each line, each mapper computes the frequency and prints out the frequencies. Okay. The letter count each of the mapper will print. So let's say mapper 1 says these many, mapper 2 says this many, or you can say this, and because these numbers look very bloated. Okay. All right. All right. Now, so all mapper 1 will do is, say there are multiple mappers in the running. We created a MapReduce program. Each mapper's duty is to print out the frequencies in the given data. That's all. All right. And what will mapper get as the input? Each line at a time. One line will be given by Hadoop. One line will be given by the Hadoop to your mapper code, which will basically compute the frequencies and print it out. Okay. Frequency, when I say frequency, it means that the letter is the key and the value is the number of times that letter has occurred in a line. All right. And after summation, this will look like this. Okay. And right, right. So each of there are two multiple approaches. The way one is the way we did word count, in which all our mapper did was word and a number, word and a number. That's all it printed. The, in the similar approach, we could also do that instead of mapper applying any logic, if it does, kind of a letter and one, A1, B1, C1, and so on, whatever letter it encounters. One is that approach. Other is this approach where each mapper is also trying to compute the frequencies. Okay. So, and at the end of it, it sums the values. Okay. So think about both the approaches. One approach is your mapper is just printing A1, B1, and whatever letters it's encountering is just printing those words. Okay, those letters. Second is it computes the frequencies and then prints out the key value, key and the counts. Okay. So which approach do you think is better? Anybody? So approach one is, let's say in approach one, our our input is, okay, and let's say Sandeep Giri. Okay. In approach one, our mapper is giving out S1, A1, and 1, D1, E1, E1, P1, and G1. Okay. In approach 2, in approach 2, it prints out something of this sort. It computes the frequencies and then prints it out. So Chandra says it will vote for the approach 2, and so will Morgan. Right. So the second approach is a little better in the sense that the transfer of the data will be lesser. Okay. Because this one will result in lot of records, while if we give 20 lines at a time to our mapper, we can configure that part in MapReduce. So if we say we give it 20 lines at a time to the mapper, then this will be just 26 lines at most. While this might become, something of the sort. It might become, say, 80 into 20, which is 1600 lines. So when the data from mapper is collected and is sent to reducer, right, the data will be lesser in this approach. Okay. And why we have taken this approach? Why are we trying to retain, maintain a 26 numbers in the memory? Because that's easier. Why didn't we take this approach in word count? Because when you do word count, the hash table which you form of key values is going to take a lot of memory as compared to our array. Okay, as compared to our array, the hash table is going to take bigger memory. Yes, that's correct, Chandra. Right? So now we have this approach. So, so the mapper is going to do this, and reducer will do nothing but count the occurrence of the character. Count this, will do the summation of each character. All right? Sounds good to you? If you have watched our the other one, the streaming part, we talked about streaming last time. So try to do streaming. Try to use streaming to solve this problem. Okay? If you have done it, make it work. And also, whenever you run mapper reducer, try to compare the results. Okay, as the map reduce process finishes, it prints out all the statistics. All right, so this is fairly easier. Now a little bit difficult question. Find the anagrams in Hughes text. Okay, an anagram is basically a different arrangement of letters. Okay, in this question, cat, act, and tag, these are the only anagrams of each other. The anagram does not need to be a good, really dictionary word. In our example, all it needs to be is in the input data. Okay. So I saw Murugan's question, Murugan's suggestion for this. I'll. Has anybody else submitted? Because I saw only one. Others are submitting. Okay. Okay. Roshan has submitted. Shashi has submitted. Puneet has submitted. All right. So maybe I'm missing something. Okay. Okay. All right. We have got Chandra also and Morgan also. Okay. Puneet is there. Prithvi is there. Sushant. All right. So I saw Morgan's approach, and we'll talk about that. All right. All right. I see Chandra's approach. This looks good. All right. So we have. All right. This is also good. Who is this? This is Puneet. How come I don't see Roshan's? How come I don't see Roshan? Oh, the first one is there. The first one is there. Ah, Okay. So yeah, you're also right. All right, all right. So right now, as per your answers, the general answer is this one, this one. Okay. So basically store the actual word and sort the word, the letters of the word, and keep that as a value, keep that as a key, and the value as the actual word. That is correct. There is one other approach. The So there are basically two approaches. One is sort the letter, sort the letters. Other was, all right. Yeah, I can see. I can see your answer, but I cannot see the answer to the second one. Only the first one is available. All right. Now the second. Okay. So most of you have an approach that sort the letters of the word, make that as a key, and take the actual word, put that as a value, and that will be the result. Now the second approach is, all right. So basically you are on the right line. Can somebody tell me the whether this approach is good or bad? This is interesting actually. All right, I had an approach here. Yeah, this one. Okay. So here the idea is that take the word, form all possible permutations of the key, and then so this approach will also work, but you will have to do a little bit more engineering. Okay, so in this approach, what Morgan is trying to do is read each word from the text stream, find all permutations of each word by rearranging letters and creating the key value pairs using each permutation as the key and the actual word as the value. For example, for the, he will form these many keys. Okay. Now the first problem with this approach is if for a for a 10 letter size, 10 length word, how many permutations would be there? 10 factorial, right? Yes, that's correct, Roshan. Second problem with this is, so each word, imagine number of words being generated per word is too high. Okay. So, okay, let me again say, uh, let's say the cat tack act. Okay, let's take this word. So for the, we have generated all combinations. Okay, the, so we generate the, and we say one, and we say the actual word. Let's just look at this, what I'm trying to say. And then we say EHT, and we say zero, and we say the. Why I'm putting 0? Because this is the actual word. Okay, so that in case it gets repeated, then we know which one to count and which one to ignore. All right. So this way you can, if you think about it, you will need to differentiate between the actual word and the rearrangement. All right. So the biggest problem with this approach is too many keys. Although the approach is correct, but it'll form too many keys. Okay. If on an average, if words are 5 factorial, I mean 5 letter long, that means for each word we are generating close to 120 keys. Okay. Is it 120? Right. So, we are actually multiplying our data by 120. So that's the only problem with this approach. Murugan, is that clear to you? All right. Okay. So for those who haven't attempted yet, let me explain the whole problem. This input, this line in the cat act in tag, your mapper will convert. This is your code. Your mapper will convert it into this sort of key value pairs. Okay. And what does it mean? Each word, when it's sorted, when the characters are sorted in this word, they become like this. So EHT and value remains the actual word. We took cat and rearranged the letters of the cat such that they are ordered. Why? Because why did we do that? Because we are trying to find anagrams, and all anagrams have exactly same set of characters. Okay, if we somehow can arrange we can somehow prepare a key out of all these arrangements of word such that that particular key is same for all, then we will be able to bring all these anagrams together. Okay, so one of these approaches is just sort the letters. So basically by sorting the letter, all we have done is we have done an unarrangement, unrearrangement. Okay, we have killed the shuffling of the letters. Basically an anagram is the letters arranged at various places. We have just made all the arrangements same. Okay, so that we can bring them together, because the way MapReduce works is it brings all the values for a key together. Okay, it sorts the data based on the key and hence brings all the values for a key together. Sounds good to you? Okay, how do we know we need to get EHT for the, and why can't HTE? Okay, so what we have done here is we have found the key after sorting the letters. So in alphabetically, E comes before H and H comes before T. Okay, that's why. Similarly, in case of cat, we have done sorting of the letters. So if you sort the letters of cat, A will come before C and C will come before T, right? A, C, T. All right. So we have basically made sure that all the letters are in the same order, because we know that anagram is nothing but rearrangement of letter. These are the same letters put at various positions, and that's all. Okay. Now this process Now, Roshan's question is why not have the actual words as the key? So if you have actual words as the key, what mapper will do is mapper will sort sorry, the output of the mapper is sorted by Hadoop based on this key. And our objective is to bring all the values for a key together, right? Our objective of this MapReduce exercise is we want to bring all the anagrams of a word together so that we can print it correctly. That's the objective here. And to bring all the anagrams together, we need to form a key which is same for all the anagrams of a word. Okay, and that key is formed by sorting the letters of the word. Because if we form the key, all right. So this is clear to everyone. This is clear to everyone. How does the reducer concatenate various values for a single key? Okay, that's actually pretty simple. Okay, so reducer generally looks like a function. So when you write a reducer, when you write a reducer, okay, and okay, one more difference is, okay, let me just take a break. Or, yeah, here you can look at this here. These are the keys. These are the keys after sorting. Hadoop took your output at this stage here. Your mappers, multiple mappers together form this kind of output. And this straight line is basically what Hadoop did for you. Hadoop did this sorting. If we are talking about streaming job, you will get this form of input for your reducer. Okay. If we are talking about the Java kind of map reduce, then you will generally get this kind of input. Okay, automatically grouped together. Alright. In case of a streaming job, this is what you get. And in your streaming job, all you need to do is keep on reading a word until the next word is different from what you read last time. Okay. So the moment you hit CIT, you print out all the words you have so far gathered. Okay. You will print out all these three. So in case of a reduce in streaming job, this is what you will get. In case of the streaming job, in case of Java, you will get this kind of input. Okay, these are the array of values, and this is the key. All right. Yes, that's correct, Chandra. So here, this is straight, right? In this, you will write a code. Your reducer will look like your in case of a streaming job, your reducer will look like this. Okay. Let me try to write something. I'm trying to write it in Python. For line in std in, okay, we say key comma value equals line dot split. Okay, and you got key and value, and we say if key not equal to last key, we print values, else our last key equals this key, and we say values dot push values dot append value. Okay, that's all. This is the kind of thing we have to write in our reducer. So although it's pretty straightforward and simple, it says that split the for each line in the input, split it by tab, and if this value, if the key is same as the previous one, say imagine you are here, and also at every time what you need to do is you need to say values equals empty array and key equals null. Alright, so this is a pseudo code, and this pseudo code looks like Python. I've written it for the clarity sake. So what am I, so this is clear, right? This is what you will do in the reducer. And in case of a Java code, in case of a normal reducer in the Java code, this is the input you will get, and hence you will say, you will say, let me just try to, my reduce, and here you will get some sort of this format. I'll talk about this later. This is you will get as an input. This is what you will get as an input. This is key and the values. And now it's up to you how you append this. Okay. You can say join these values with comma and return it. Okay. Okay. Right. So this print means we are giving that as an output. Yeah, that's correct. So yeah, so this is not a perfect code. This is not a perfect code. There is a mistake like and values. So the first value might get missed and all. All right. So this is clear, right? So normal MapReduce, the Java one, gives you the key and the values together, while in case of a streaming job, you get keys and values and you have to group it by yourself. All right. All right. So everybody clear about this anagram problem? All right. It's good to spend time on this because lots of people they don't actually attempt any other thing than word count, and people start believing that MapReduce is actually meant for only word count. All right. So that was our second attempt. Now the next one is fairly simple. A file contains the DNA sequences of people. Find all the people who have the same DNA. Is this simple? We want to find all the people such as user 1 and user 4. Their DNA is same. You want to find out all such people. What will you do? Yes? Are you sure the user has the key? Right. So it will be the DNA as the key. Shashi, yeah. So doing it without MapReduce is actually a pretty straightforward job. But the idea is to do it using MapReduce job. Okay. Yeah. You can give attempt now. So what should so given this kind of input, what will your mapper do? What should your mapper do? This is your input. Okay. If you just print it out as is, which means, which I understand correctly, you are saying let the user be the key. So Chandra, you can submit it again, no issues. All right. And also, as soon as you log in, right? As soon as you log in, you will see all. If you click on use my user account, okay, you will see something of this sort. Okay. Here you can click on my results, and you will see all the results. Okay. That's correct. So the key as DNA and the user as values. Mugan, are you okay with this? All right. So your all your mapper has to do is make the DNA as the key and the user as the value, because what will Hadoop do? Hadoop will bring all the values for a key together. So all the users for a DNA will come together if you make DNA as the key. Okay? Yes, in this way, reducer will not have much of a work to do. That's correct. All right. Now, this is clear, right? Should we move on? All right. So the first one is the third A question is pretty straightforward, and you actually the main role is being done by your mapper, and the mapper does it by making DNA as the key so that all the values will be aggregated together by Hadoop in order to give you the results. All right. Now, a file contains the DNA sequences of the people. Find all the people who have same or mirror image of DNA. Has anybody attempted it? Okay, okay, that's interesting. So let me have a look. All right, let me have a look. Okay, not yet. Okay, read each value and find also the reverse DNA sequence by letter and order those two. Wow, wow, great, great. This is good. And concatenate and assign it as the key and the user as the value. Perfect, perfect. So what he has suggested is take the take a DNA and take the reverse of it, then order these two DNA to two words and then concatenate it. Do you need to concatenate it? My question is, why don't we just pick up the first one? But still, even if you concatenate it, this is good enough. All right. Excellent. Excellent. Now let me have a look at the other question. I'll show you. I'll show you it will work. That is excellent. Okay. Now, yes, yes, that's correct. So all I was saying that so you took a DNA, you reversed it. Now you have two words. One is actual DNA, other is reverse of it. You pick up the first one out of it, or you just concatenate these two. Just concatenate these two in the order whichever the sort these two words and then concatenate them, right? So even if you do not concatenate and you just pick the first one, that is good enough. All right. Now this is this is ACGT user one. Okay, not this one, not this one. Let's move on. Okay, this is good. This is good. Excellent, excellent. So I'm happy that you got it correctly. Whose book is this? It's Puneet. Excellent. So yeah. So he has done minimum of DNA and reverse of DNA. Excellent. Now, all right, all right. So is anybody having different approach than this one? You want me to check your notes quickly? Morgan, Prithvi, perfect, perfect. This is also good. This is also good. Excellent. So almost all of you have answered this, and that is min is basically the smaller of the two. Okay, Santosh. Okay, let me have a look. All right. So okay. So have you submitted? Actually, I don't see it today. Today, this week, yesterday. Okay. Hmm. So yeah, would you be interested to filter on username? Yeah, I would like to. As yeah, let me do that. Oh, how come it's not visible? All right, so let me have this look. DNA. Here, take each line and break into words. Key DNA value. Now parse each line again and insert into output as below. Okay. Okay. So your approach is similar, but actually we don't need to do it in the reducer. Okay, okay. Each key, this. No, I did not get this approach. Take each line and break it into words. Okay, these are two words we have broken into DNA and the user. We have got two words. Now parse each line again. Oh, you mean to say for each word, each word, yeah, that's also right. So let's say this one, what you're saying, insert two key values into the output. One is DNA and the user, and other is reverse of DNA and the user, right? Okay, that approach is also correct. That approach is also correct. It just you have to do a little bit more flagging, saying that this was the actual one, this is the reverse one, and so on, and then deduplicate in the output. Yeah, as you have said, that unique values. Yeah, yeah. So we have got how many approaches? We have got three approaches in all. Good, good. I'm very proud of this thing. But, yeah. Good, great. So basically, so okay, let me go through one approach. Which so we got three approaches. One was concatenate the DNA and the reverse of the DNA in the increasing order, meaning ACGT and the reverse of it is TGCA. So we'll form the key as ACGT dash TGCA. Okay, that is one approach. Second is just pick up the first one, the smaller of the two, smaller of the DNA and the reverse of it. Whichever is smaller, you just make that as a key. That approach also works fine. Now the second approach was that third approach was you print out the key as the DNA and the value as this, and then you print out second key as reverse of it and then value. That approach is also correct. It's just that in output you might have to scan again to figure out which keys you need to eliminate. Okay, you have to find out the unique and a little bit more work you might have to do. And interestingly, that approach, Santosh is what this approach of forming two keys was my first attempt onto this problem when I was actually solving it. All right, so after a careful examination, I'll realize that this approach is better in terms of the complexity. So we take a word, say ACGT, then we take a DNA, say ACGT, we reverse it, and say ACGT is reverses as TGCA. We take the minimum of it. Minimum as in when you compute minimum, you compare the first letter with the second letter and a first letter with the first letter and so on from left to right. Okay, just the way in case of our numbers we do that. All right. Now we pick up the minimum out of it. So this becomes our key. This becomes our key ACGT, and the user becomes value. Okay. Now what you need to understand here is now those users whose DNA is either identical or is mirror image, they will all have the same key. Look at it here. User 4 and user 1 are having the same key, and similarly user 2 is also having this same key. What happens if we have a space in the beginning? Which space? Okay, Prithvi, let me have a look at Prithvi's also. Mhm. Anybody? Okay. So give it a thought. Let me just go over Prithvi's approach also. I skipped that. Can anybody help me out with this? So his approach is split input into two columns, user ID and DNA sequence. Pick the records in sequence. In an index, our operation having DNA sequence and user ID list. Okay. 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 But here, if you notice that, okay. So what you're saying is that you are not using MapReduce here, right? You're using a normal standard way, is it? Okay, okay. Yeah, in that sense, it would be okay. But again, it'll be actually too much of intensive if you scan through the index again and again. Hmm. So this index, what we are talking is something is a little bit of a worrisome to me here because this is what will overflow your memory. All right. So for exactly this kind of a thing, uh, because this is good if your data is smaller. The data grows bigger, you cannot use the same approach. You might have to figure out a way to move the stuff to MapReduce. All right. Okay. So basically, in MapReduce, we are trying to form a key such that all values come together. And here we are forming the key by finding the smaller of DNA or reverse of DNA. Okay. And here we go. And reducer doesn't have much to do because everything is anyway done by the our main job. All right. Now moving on. Should I move on or should do you need any more clarification on this problem, Prithvi? Yes. Should I move on? All right. All right. So now we are talking about the fourth problem. Who has attempted this fourth problem out of all? And okay, good. Okay. Anybody else? Puneet and Morgan, Prithvi and Chandra. All right. Let me have a look from the left to right. Shashi hasn't attempted yet. Okay, so here is first one. Assign key for every value in the voter as the key and value at 0. Okay, so the problem statement is given list 1 and list 2. Find out the vote count of each person. We are given voter and votee, and we are given person and the worth. Okay, you are given the voter as the worth. Okay, assign key to every value in the voter as the key. Okay, and the value at 0. Okay, and for and a key for every value in votee. Oh, okay. So here when you say look up on the list, that's where it raises questions. Here, reason being, if this is big data, then looking up will not be an easy task. It is not going to be easy. All right. And this is Puneet. Okay. So Puneet says that map use two tables, make a pair of OT and worth. Perfect. OT and worth. Yeah, but to reach to this level would require a little bit more mechanics. To reach to that level will require a little bit more mechanics. All right. Join the list one. Okay. Yeah. The question is, how do you join this? How do you join this? This data is lying in the file system, and this is we are not going to use your standard database. We want to use our MapReduce. Okay. Wow, this is good. This is good. Merge both the lists using voter and person ID. Good. Sort and merge this. Feed this. Good. Good. All right. All right. So yes. So this is correct. So this answer is good. Anybody else wants to check? I went through your solution. And Santos's question. How come I don't see it? Santos, what's your ID? This one. All right. All right. No, it will actually require a little bit more engineering. Alright, so out of it, this is the one it looks good to me, which would actually work. This one. It's just that this needs to be broken down into two passes of mapper and reducer. The last exercise is all about joining the two data sets. First we join, then we group. So, okay, alright, so I will explain it here, that approach. So objective is to find the total vote count based on the worth of people. Okay. Now the first step would be we just take these two files as input files. Okay. Where the key is in the first one the key is voter and second one the key is the person. Now, for each voter, this data will get together concatenated like this after MapReduce, because this is our key, and the value is either the voter or the worth. And hence, at the end of the MapReduce pass, we will have something of this sort. Okay? Or you can also do like this. After we have run map, and Hadoop has taken those values as map, and our mapper gave out this output. Hadoop brought out the keys together, values together for a key. Okay, so this is what we'll get. We get 5 BC and so on. Okay, now our reduce, the function which is reduce, what it does is it takes up all the values for a key, say this one, and prints out. For this one, it will print out something of this sort. It says, what does this table signify? It signifies that A has voted for B and C, A has voted for B and C, and A's worth is 5. Okay? A has voted for B and C, and A's worth is 5. This is the line which states that. Now, reduce will be given one key and the value at a time, all the values at a time. Now, it will be reduce's job to take it further. Now, what does reduce do? Reduce basically takes up this array, and by virtue of this array it assigns the numbers to all the people who have been voted by A. So because A voted for B, now B will get 5. A voted for C, C will get 5, and since A has voted, so A gets nothing. So for first key, the reduce converts this into this format. Sounds good to you? And for second one, it converts it into this format. It says B voted for C, and hence C got a value of C1 and B got nothing. Okay. Basically, reduce is trying to convert this table into the worth added to various individuals because of this voting. First column in the key array always be the worth value. That is very good question. So not generally. Okay, not generally. You might have to either sort by yourself here in the reduce, or you might have to join these two tables such that the list one is joined before list 2. Okay, but don't rely on this. Inside reduce, you might have to sort this data. Okay, sort this data. Now, sorting this data in memory will might create a problem. So we will also think about what else could be done in order to avoid these kind of memory overflows. Okay, we could scan this array twice. We could scan this array twice. All right, and find out the worth. Which join or merge? Yeah, merge basically. We are merging, not joining. We're merging the two files. You're right. All right. So this operation is clear, right? So first we form this kind of a way that A whose worth A is the key, and its worth and the people it voted are in the values, and reduce converted this array into this format. Okay. Now rest is pretty simple. All we need to do is run another map phase, and in second phase, reduce phase, we just sum it up. This is the values of people will get. Okay. Here for the next set of map, the f- the key is very clear. The key is very clear, and the value is the worth contributed to by various people for B. So B was okay. So is it clear to you? No? If you want me to explain again, I can explain again. Okay. Okay. So Mugan, it basically is Hadoop, right? I'll tell you. Yeah, that is. So Chandra has sent a message saying there's a lot of unlearning to do. Yeah. In the beginning, you need to do a lot of unlearning here. But trust me, you would not require to do this. Okay. Because after this session, we will be talking something about, we'll talk about something called pig and hive, where you can utilize your SQL skills, what you learned. Okay. All right. So we'll talk about uh, SQL, and so basically this is very important. Although I can assure you that you will not be doing MapReduce too much, but almost everything, even the latest frameworks such as Spark, they all have MapReduce kind of a syntax. Okay, that is why I want to spend more times on this, and I will also emphasize a lot on what to uh, on learning MapReduce. All right. So almost all the things which you could do with SQL, you can do with MapReduce. All okay. So had somebody asked. Puneet is saying I should repeat once. Okay. So you got one list where list 1 contains voter voted for somebody. List 2 contains the worth of the person. Yes. What happens when a person has no worth and get voted? Yeah. So it doesn't matter, right? It doesn't matter. The problem would occur. So Prithvi's question is what happens when the person has no worth and get voted? Okay, it doesn't matter in that case. If you see here, let's say let's say F is there, right? F got voted by C, but F has no worth here. Is this what you're talking about? Okay, so your question is what if there is a person called H who voted for A, right? And H has no worth. Is that you mean to say? So you mean to say C voted for F, C has a worth here. So you are saying if C votes for F, if C votes for F and the C has got a worth. Is that what you meant to say? So in case of H to A, let me think if that works or not. Yeah, that will be a problem because what will happen at here is you will see it'll be something of this sort. All right, and there you will not find value here to be added to A, and then maybe in this reduce you will have to put an extra clause saying If in this array you do not find a number, then as a consider a 0 as its worth. Okay, so these are boundary conditions. Very good catch, I would say, if that was your point. All right, Prithvi, are you with me or you're typing something? All right, now, all right, so should I? Okay, so what happens in case F voted for C? That's what I was coming to. Now, if F voted for C, now there'll be a that's a very good point, I would say. Okay, so we'll have F here and we'll have C here, right? And in case, and at the same time, we'll have F here and only C this time, right? Which means this our logic will fail. The only thing that could save us here is this reduce function, in which we can say that if in this array the number is not found, just assign this as 0. Okay, so this is what you will get. All right, so we will have to do a little bit more engineering in the reduce function, where in case nobody voted for somebody, or in case somebody voted but it has no worth, and so on, those kind of boundary conditions you will have to check here. All right, so what I'm saying is, in case the worth is not given, assume it 0. All right, so should I explain further, or is it clear to everybody, the voting problem? So here it refers to, when we say HDP, it's basically Hadoop is using its own internal algorithm to sort your data. When I say SDP, it means Hadoop. Hadoop takes the output from your mapper. This is your output of the mapper. Maybe multiple computers, multiple mappers on the same machine, and combine them together to form this. This is the role of HDP. All right. It could be in memory, partially it will be on the disk. All right. So we had taken these things last time. In case of a streaming job, if it is okay to have no reducer, okay? And in case there is no reducer, still there will be a sorting. Reducer means you don't want to reduce the values. Whatever values coming from the mapper, you want them to be pushed to the output. Okay, if your reducer code has nothing, I'm talking here about streaming job. In case of if there is no reducer, the data will still be sorted by Hadoop. Okay, the keys will be sorted by the Hadoop. It's just that there is no reducer to summarize it. In case you do not want heavy lifting of sorting, sorting requires a lot of heavy lifting. If you do not want that to happen, all you need to do is specify a flag called -d mapred reduce task equals 0, and then there will be no output. Sorry, there will be no sorting of the keys which are the result of the mapper. All right. Now, next is map will decide the number of output files. Okay. Generally, it's the reducer which decides how many output files are there. For each reducer, there is always one file. And in case you want to, if you don't specify the reducer and also you specify that no reduce should be executed, the total number of output files will be decided by the maps. Okay. All right. So number of maps, when Hadoop is executing your task, you give Hadoop four things. First is, this is my input data, this is my map function, this is my reduce function, and this is where you need to store the output. Okay. In case in case in case of map reduce, it is going to execute these maps on multiple machines. But the question is, how many maps would be created? Okay. It's a function. Generally, it's defined by how many blocks are there for each file. And for those blocks, basically it depends on those number of blocks. And you can specify by yourself also. You can force Hadoop to execute your task on multiple nodes, have multiple tasks at multiple machines using this function if you set in the configuration. All right. Now another question is, how many reduced tasks you need to have in order to have the best performance. Okay. So it's a general question which lots of people keep asking. So generally, you keep the reduced task total, because the reduced task is something you can specify. Okay. As per my personal opinion, what I do is, the way I do computation of reduced task is fairly random, fairly hit and trial. Meaning, in the beginning, for the same data on the day zero, I will try with, say, two reducers. I'll try with two reducers and see how much time the output has taken. Okay. I- if it is taking too fast, but you just note down the time taken by two reducer tasks. In case, and just note it down, and then next thing I would do is I would run the same task with, say, 10 reducers and see the feedback. And we do a little bit of a binary search and to figure out where is my task. I mean, how well my task does on various kinds of reducers. But that's more or less a hit and trial method. That's not something you should answer to people when they ask you, but that is how it is generally done. Okay. So, and also this approach of hit and trial is not good if you are not sure, if not good for the first few times. Okay. If you are not sure that this task will get executed again, then it doesn't make to do hit and trial. A better way to do is do a little bit of computation. Okay. The minimum number of reduced tasks, you generally keep it to 0.95 into maximum tasks possible. Okay. So your number of reducers are generally between these two. 0.95 into maximum task to 1.75 into maximum tasks. Is it? I look sleepy to you? Okay. Okay. I think it's a time for break. Yeah, sort of a party. Never mind. So let's have a break and then come back. All right. I don't want to spoil it. All right. So no worries. So I'm back, guys. Are you back? Great. So yeah, as should we start now? Looks like others are not here. All right, then let's start. Great. So we were talking about number of reduces before we took a break, and yeah. Now I hope I don't feel sleepy anymore. So the maximum tasks are are something computed as number of nodes into your configured value of tasks. The default configured value is 2. Okay. So let's do a little bit of a computation. So let's do a little bit of a computation. Okay. Okay. So now by default, there are these many tasks that could be executed on each node parallelly. Okay. So it is 2 generally. If you have 4 nodes, so it is something like 8. Maximum number of tasks that can be executed on your cluster is 8. Reduced tasks we are talking about, which means your number of reducers have to be somewhere between this to 1.75 into 8. Okay. And hence it is going to be 0.95 into 8 is around 7. Okay. And 1.75 into 8 and 14. All right. So somewhere between 7.5, I mean 7 to this, you can say 7 or 8. Okay. These many reduced tasks you can execute on 4 nodes cluster. All right. In case your each individual machines are little high end and you're okay to run some 10 tasks in parallel, so you configure this in your MapReduce that execute maximum number of reduced tasks around 10 and so on. Okay. So is this calculation okay with you? Any questions on the calculation? Yep. All right. Because this is something which everybody seems to be confused about. Okay. If you have the other thing is, if you have more and more reduces, the framework load will increase. Okay. Framework load will increase because too much of shuffling will be there. Trans the transfer of the data will be more number of connections in your network. But it is faster if you're reduces are more, basically it is faster because more number of nodes are trying to compute the reduces. Second, there are lesser chances of failure. There are lesser chances of failure because it seems that in the Hadoop 2.0, the reduce phase itself is also very well load balanced. Okay. In case one fails, the other one is given the work to execute. Okay. All right. Let me note it down. All right. So we discussed this last time, and if the job can be done by a single machine, yeah. So Roshan's question, I was trying to answer that one. Basically, the more the number of reduced tasks is there, the there will be more number of reduces parallelly happening. If in case one fails, the Hadoop 2.0 is basically able to have the same reduce run on another machine. Okay, which means that only small part is getting hurt, and hence the work can be performed on multiple computers parallelly. All right. So so effectively, there are other optimizations also done in case of MapReduce, such as while the mapper is spitting output, reducers start working and start processing first phase of data. So those kind of optimizations have been done other than the load balancing. All right. Now there are many cases. There are many cases when you should not be using MapReduce. First, when your next step depends on the previous step. When your one mapper depends on the data from another mapper. In those cases, it's actually very difficult to use MapReduce. For example, if you have to do Fibonacci series. And what is Fibonacci series? Nth value is a summation of n minus 1th value plus n minus 2 value. Previous last two values, if you sum it up, it results in the next one. Okay. So that is Fibonacci series. So the the reason why I have given this example is whenever you try to compute a value based on previous values, it does not make much sense to use MapReduce. Basically, any such task where this kind of behavior is there, previous values need to be used for the next values. In those cases, it's very difficult to use MapReduce. Similar is the case with the dynamic programming. In case of a dynamic programming, there is a central cache. This is a central cache where the previous steps keep on updating the values in that cache. Okay. I'm trying to simplify what do we mean by dynamic programming. In case of a dynamic programming, the values computed in the previous steps are stored and those values are reutilized in order to find the final value. Okay, so mostly in case of dynamic programming, it becomes very difficult to distribute the work. Okay, similarly, the Fibonacci series. Any questions? Also, in case your algorithm is depending on a shared global state, there is something wrong you are doing. All right? Or your problem is not at all suitable for getting it done on MapReduce. Although it is completely okay for your Python code to connect to a database inside map or reduce, but I mean it's completely possible because the script or the program you're going to execute, it can do anything. It can download data from anywhere, it can connect to the database. Your mapper code can do anything. But what would happen is, when imagine that for each line hitting a database somewhere is actually a horrible thing. Imagine this: you have few hundred terabyte of data, which has got say thousands of mappers running parallelly on your cluster, and each mapper, when they encounter a line, they are hitting one MySQL server. Okay, and now if all of these mappers are going to hit the same MySQL server parallelly, that MySQL server will die of the load. I mean, it will be too much of overload onto that server. So it does not make much sense to depend on a global state. If your code is depending on global state, then there's something wrong with it. Either your problem is not suitable for MapReduce, or maybe you need to think through your solution. In last few examples, if you ask somebody who does not know much of a MapReduce and who is just learning it, there are high chances that they will all end up with some sort of a shared global state. Okay. The way some of you suggested, that pick up a value from list 1, look it up in the list 2. So most of the people, what will they do is they will end up having list 2 in some database and start hitting it. Okay. So in case this kind of thing is happening, just think through your problem. Either you have not converted your problem properly into MapReduce, or your problem is not suitable for MapReduce conversion. All right, those are the limitations when not to use MapReduce. Before we start Java thing, let's go through few things. To test MapReduce is actually pretty straightforward. First and foremost, test it on very small data. Okay, small data as in say few hundred lines, and few maybe few thousand lines. Okay, now the problem with small data here is, again the voice breaking. All right, all right. Okay, so is it better? Is it all right? If it happens again, we'll change the net connection and then see what happens. Okay. All right. So now here we are. Now question is, whenever we are doing smaller data, you generally work on a sample data. Okay. Remember this part. So whenever we are running our code against a set of data, you generally create a random sample out of the input data. Okay. And because running on first 10 lines or last 10 lines of your input file would always give you very small or very biased results. Okay, so whenever you are working on a small data, even duration of testing, you do a random sampling of data. Okay, almost every tool in case of a big data domain provides you a way to find random sample of the data. We will talk about it when we discuss pig. Okay, so find a random sample, separately test your mapper and reducer. After you have separately tested your mapper and reducer, you can run them together using this way. Okay, here we are talking about the streaming job. In case of streaming job, if you have written a mapper and you have written a reducer, you can use this sort of a command to actually solve your problem. Okay, so how do we test a reducer? That's Chandra's question. The way that to test the reducer is this. Oh, you mean to say how do we independently test the reducer? Okay, so you form the input which will be giving a sample input that reducer will receive, and and then see the output reducer has done. Okay, now have a look at this. So you first, in case of our word count example, you will first form mapper input, mapper expected output. These are the things you have formed. Similarly, reducer input. You will form this kind of input upfront before going further, and reducer expected output. All right. This kind of thing you will do. And to test your mapper is simple. Whatever input is there, okay, let whatever input you have saved it in some input file, you can simply say cat my input file and then run the mapper. This will give you the mapper's expected output, and compare this output, compare the output of this command against what is the expected output. Similarly, in case of a reducer input you form a little bit, and similarly you should just say reducer input. You just create some sample input. Okay, here let's say word 1 1, word 2 1, etc. Okay, this is mapper's input. Not this. Mapper's input will be once there was a king of the jungle, some sort of this. Okay, and expected output from this is once one there one was one a one king not kind, and so on. This is the expected output. So you just generally form these output by yourself and then compare it. Also note that when you compare the output of the your mapper or reducer, it is okay even if these are not in different order. Okay, now reducer input, you just form this input whatever you have formed here, say a sorted one. You form a sorted input, say apple one, banana one, and say banana one again, and so on. Okay, the expected output out of here is 2. That's all. Okay, and you run reduce. Sounds good to you? So you form these kind of input and mapper input and output, and then you run it across through your program just to test it. Okay. In case you are from Java background, this whole philosophy is first further parameterized and made more made more formal. This whole approach has been more formalized using something called MR unit. We'll talk about this. The other important thing when you're talking about big data, this is probably one of the very important part. Let me ask you this. Using, let's say there is an algorithm which claims to produce the best sort of recommendations. It takes all the data from people who have voted for movies. There is a website, say IMDb. It has taken the movie ratings from all the people. Basically, it has user ID, movie ID, how much the rating each user has given to it, and on what date did they rate the movie. Now, given this data to you, you wrote some brilliant recommendation engine. How would you test this kind of a recommendation engine? Anybody? Meaning, how would you test an oracle? Oracle is somebody who predicts the future. How would you test that somebody who is predicting the future is correct? Anyone? Right. You ask something which you already know. Okay. Okay. Meaning, so let's imagine that there is this website which has name of the three columns, movie underscore ID and user underscore ID, and then there is a third column name rating, and there's a fourth column called date of rating. Okay, there are one, so say 1 billion entries in this. Okay, 1 billion such entries, and recommendation engine takes this and gives you the recommendation. So what will you do in order to test it? Okay, so the general strategy is slice this data by date of rating. Slice this data which is ordered by date of rating. In case it's not ordered by date, order it. Okay. Use this algorithm to generate recommendation on first half and compare it compare it with second half. Sounds good? Okay. So as you yourself said, ask something which you already know. And what you know is 1 billion entries of user ID, movie ID ratings. Okay. You know that people have rated these many. So what you do is take half billion, you first half billion, and give it to this algorithm which claims to generate the recommendation, and whatever recommendations it has given, compare it with the actual one. It says that Santosh will like Matrix, and the chances of Santosh liking Matrix is 5.0. And then we in the second half we have the data. whether Santosh liked that movie, watched Matrix or not. If Santosh watched Matrix, then we say that, oh, this is good, this algorithm is good. Okay, we compare the result of the recommendation with the second half of the data. Okay, and how do we compare? We generally compare by the way of root mean square value, meaning we compute the differences we compute the differences between the suggestion given by the recommendation engine saying Santosh will like matrix 6 and actually Santosh like 7. So the difference is 1. So modulus is 1. Whether 7 minus 6 or 6 minus 7, we have to do the modulus. And we do the summation of all this modulus and then say that, oh, this much is the deviation in this algorithm from the actual one. Yes. So Prithvi's question is, the change in the people's mindset will result in different values. That is correct. But that deviation in the mood is fairly I mean, that will be outnumbered by the actual data. If you have half million entries, then you will is that actual values will overrun the other deviations. Okay. Also, also, this algorithm is just one example I have taken. People take lot more data into account when they are doing the recommendation. All right. So, okay. And to you will be surprised that the success of even this kind of algorithm is actually is actually pretty good. The success is around 90%. Okay, if you read a little a bit about things like Netflix competition and all, you will get to know that. All right, but the thing is, most of the big data problems, the real big data problems, is about prediction, is about forecasting, or is about past data. Okay, is about the analysis of the past. In case it's analysis of the past, then these previous steps are good, but in case it's about the future predictions, then you will have to slice the data into half, split the data into half, run the algorithm of prediction on the first half, compare the results of prediction against the second half, and then formulate a way to quantify maybe a root mean square value, maybe a summation of all the deviations by ignoring the negative or positive. Okay, so those kind of predictions you can do. Okay, Prithvi's point is, this is on the assumption that most of the ratings is got closely after the movie has released, and number of ratings reduces. This is on the assumption that most of it is got closely after movie has released, and I did not get this assumption. Maybe I need to think a little through. This is on the assumption that most of the ratings is got closely after the movie has released. Okay, okay. We can discuss it, but the overall objective here is that whenever you are testing predictions, this is what you do. All right. First is sampling of the data. Remember, always whenever you're dealing with testing the big data, do not try to write your algorithm on your own data set. Here, I have here in just now a minute ago, I tried to just yes, lesser the root mean square value, the better will be the prediction. Root mean square value is summation of root of, okay, that is a different thing. Talk about it. Okay, so yeah, you're right. So keep that in mind whenever because I have seen a lot of people's algorithm failing badly when it comes to production. The reason is they do not take random sample. Okay, so what they do is they write their algorithm, it's running beautifully on their own handcrafted input data, and when it goes to the production it damps the whole cluster. Okay, I've seen it happening more often, and that is why we used to have a dummy cluster, still having 10 computers separately just for people to test their work. Okay, so keep that in mind. These are few important things which I believe we all miss, but it is required. Okay, now I would not like to discuss this I'll discuss in the in the next session. Okay, okay, now, all right, so you guys have done a brilliant job at answering these subjective questions, so please finish all of that if you have not finished, or code all the MapReduce problems in your own favorite language. All right, try to code all your MapReduce problems in your own favorite language. Second assignment for today, for actually this is a session three's assignment. This is important. This is important. Now, there's a huge corpus of text given to you. Okay, and based on this, you need to build a beautiful keyboard recommendation, typing recommendations. If you guys are using Android or iPhone, you will notice that when you type a word, there is a suggestion for the next word. Okay, there are say 4 or 5 suggestions for the next word. How would you build that kind of dictionary? A dictionary of this form. Given a keyword like happy, what are the next top 5 words that could be suggested to the user? Alright? And this dictionary you need to create based on a huge corpus of the data, such as Wikipedia. Are you okay with this? Is the question clear to you? Given a huge corpus of text, you have to form these recommendations that what words, what top 5 words come after a particular word. Okay? Yes, using MapReduce. All right? Yes, all these words exist in files. You can download the whole Wikipedia from here. So there is a huge story. Out of that, all you need to do is form the suggestions. Okay. All right. Sounds good to you? Should I move on? All right. So try to do this. All right. Now let me open session number 4. It's a very good and important question. We call them n tuples. All right. So in the session number 4, So solve this problem and we'll talk about it later. Okay. Now here are few questions to you. The data generated by mapper is given to reducer and then it is sorted. Yes or no? Perfect. Perfect. Now I'll put question mark. Mapper can only generate a single key value pair for an input. Prithvi says no, and Shashi also says no, I think. Anybody else? Chandra? Yes. So you can make it to everybody. Actually, your message is only coming to me. All right. So perfect, perfect. So this is correct. So mapper can generate as many key value pairs it actually wishes. Okay. The reason why almost, I mean, this question, half of the people get it wrong because because the mapper, the way traditionally it has been designed is mapping means translating one value into another, translating an array into another equal sized array by applying a function on it. So traditionally mapper has been that way, but in case of Hadoop, the mapper can generate as many keys, as many output as it wants. Now, now who can answer this? A mapper has to generate at least a key value pair. Perfect. All right. So now next question. By default, there is only one reducer in case of streaming job. All right. So yes, by default, there is a single reducer job. You can specify multiple by one particular argument like this. Okay. Second, right, that's right. All right, moving on. What is the role of job tracker, A or B? Executing the MapReduce logic or delegate the MapReduce logic to task trackers? Perfect, that's correct. The map logic is executed preferably on the nodes that have the required data. Perfect. Okay, okay, that's right. This is called data locality optimization. We will talk about it in a little more details. Now, the map logic is always executed on the nodes that have the required data. No, generally it is executed there, but not necessarily. That's right. Where does Hadoop store the results of reducer? Perfect, perfect. So this one is little tricky. Where does Hadoop store the intermediate data? Okay. So by default, the intermediate data is actually sort of useless after the reduces have finished. Therefore, it does not make much sense to put it in HDFS, and therefore it is kept in the local file system. All right. We cannot keep it in the memory completely, although parts of it lie in the memory in the beginning, but they all are moved to the local file system after some time till and they stay in the file system till reducer finishes the job. Okay. This one, anybody? Although we have not addressed it yet, I want to see what is your opinion. So there is an HDFS block. HDFS block is has a hard boundary of number of bytes. In an HDFS block, you can imagine that maybe half of the word is one block at one block. A word can be on the boundary, right? And say half of the word is in one block and rest of the word is in another, right? But when we do word count, that could have failed. We could have got wrong word counts. So, do you think the whole of HDFS block available on a node is fed to the mapper? Anybody else wants to change his opinion? So, answer is no. Okay, because we'll discuss this in detail. As I told you, the moment you can remember that there is something called physical file system in which blocks are stored, and a block is a hard boundary, which means that at exactly 128th byte it will cut it and and make it a block. It'll cut the file at exactly 128th MB and so on, which means that your data might get garbled. Imagine that half of the word is in one file, half of the word is in the other file, right? Now, if our whole block was fed to the mapper, so the one word will come as two words, which means our word count program was wrong. But no, Hadoop provides sort of a kind of a readers of this data, which gives you a logical representation of your input data. Hadoop and that logical representation is called input split. So using one block or more blocks, input splits are created and those input splits are fed to your mapper process. Okay, we'll talk about it in detail. All right, we'll talk about it, Chandra, don't worry. Now, today we are going to discuss something called MapReduce in Java, and that's where we will also discuss input splits. So, why Java, you might ask, when we could do everything in, uh, you know, when we could do everything in streaming job, why do we require Java? Firstly, you should learn MapReduce in Java a little bit because first it is primarily supported. Second, you can modify a lot of behavior of the way MapReduce happens using Java because Hadoop is written in Java. All right. So the steps for this is, if you guys have been through my Java class, have you gone through the Java recorded videos? Is for is there anybody for who the Java recording is not available in the session? Everybody had Java recordings, right? Yes. All right. So now let's start with Eclipse. So install Eclipse, download it from Eclipse site. It's free and it doesn't have any sort of licensing restrictions. So install Eclipse, create a Java project, add all the libraries provided in this Java project. See your LMS. You will see a lot of detailed. There'll be a zip file. You can download the zip file containing the whole project, and you can actually import the whole project as such without making any changes. Or JRE version is this version is needed. Okay, no worries. Now, not this one. Hmm. All right. Hmm. So you create a new project, new, and then you say Java project. This is say test 21 Feb. This is created a new project. And after that, what did I do? After that, you add the libraries here, properties, and then you go to build path and you say add external libraries. And wherever you downloaded that project, which is there, it will have something called libraries, libs folder. You just, being a little lazy, you just add all the libraries, all the jars, and you'll be good enough to go. Okay. Let me close everything else. Now inside this, you need to also do one more thing. You say properties and you change the JRE version. Why do we need to change the JRE? Because it's generally a good practice to code against an old version of Java. Because when you compile your MapReduce code and you send it to the server, because Java is a compiled language, right? So you convert your code into a binary which you send it to the user, which you should ship. right? In case this code is compiled in Java 7 and on server it's Java 6, it will not run. It'll give you an error. But in case your server has Java 8 and your code is written in Java 7, it will work better. All right? It work well. Therefore, the general tendency of a developer is to code against an older compiler just to be safe against the production times issues. Okay, all right. So here we have added our library is Java 1.6, and that's all. All right, now you create a class called stub mapper. Okay, create a class called stub mapper. I've already written it for you. Create a class called step mapper. This is the general footprint. No matter what you do, this is the kind of footprint you will always get. Okay. This is this place you see in the Eclipse. This is where you will be writing your code. Okay. Rest of rest of the things will be almost similar. The other thing is, okay, let me just take you through the code once so that you understand what's going on. It's a standard word count example first. Second, the mapper class extends something called a mapper, and also it specifies what is the data type of input key, input value, and then output key and output value. Now you might say that it's a mapper. Why does it need to take input key and value? So any mapper will get the byte count of the line byte count of the line it's executing currently. Okay, by default that is the general behavior, and then each line will be inside text, and this is the data type of the output of mapper. Okay, so stub mapper essentially we are saying extend the basic mapper. Our stub mapper is having the same behavior as mapper, and these are the various data types which we need to take into account. All right, now whatever data type you put it here, same data type will go here. You'll get the input key and input value in this format. Okay, and you'll get one more object called context, and the context is the one to which you have to give your output. Okay, now you got the input line in this value. You all you do is you split this line by tabs. Okay, tabs and spaces. Now you got a list of words. For each word we removed anything which was non-alphanumeric. Okay, we removed it. After we have done that, we converted into lowercase, and for this word we wrote it into the output. Here the output is collected by this object called context. So we are given a key and a value. The value is numeric 1 and key is word, which is wrapped in a object called text. Okay, so similar to string, Eclipse comes up with its Hadoop comes up with its own class called text, which is equivalent of a string. Therefore we convert our word into text before giving it to the context. Okay, so now ready with we are happy ready with this code. Now next step would be you write it in the reducer. Okay, now when you create a reducer, you extend a class called reduce, and you again specify the data type. It's like creating a it's like generics. It's like specifying the data type of various values while extending a base class. All right. Now there is a function called reduce. The function called reduce. You have to write this function, and you can write anything in this, whatever logic. Here, what we are doing is we are saying iterate over the values and calculate the summation and write that into the output. All right. Now the actual code is here. All right. Also notice that in these classes we are putting various kinds of error messages. The way we print sys.out.print and this and that. Once we are done with it, we create a driver. Driver is basically a configuration way of launching your map reducer. Okay. We are saying that start. This is my job. The name of the job is this, and this is the name of, okay, my mapper class, my reducer class, my various kinds of output key value pairs which I'm expecting, and partitioner we will discuss later. Here we are also specifying number of tasks, okay, number of reducer task. All right, I'm just trying to see if it has any mapper tasks, number of mapper tasks. Okay, it doesn't provide, Java code doesn't provide a correct way. Okay, the conf has a feature called change the number of map task. Okay, using conf you can do that, and as okay, using conf you can also change number of reduced tasks. Sounds good to you? And after you're done with it, we also specify the input file, output file, and so on. Okay, just just like we provided these options on the command line. In case of a streaming job, we specified all these values on the command lines. Here we are specifying these values in a separate driver class. All right, now once you're done, you wait for the completion and then exit. That's all right, now that's all. Now after you have written the code, the good practice is to write the test cases. Okay, I've written some of the test cases, you can also try. And once you are done with everything, what you do is you say file, export, and export a jar file. And then we have, this is my sg word count dot jar. Okay, now it has, this is locally available, we call it sg word count dot jar here. Good. So we exported it, now we upload it to the server using scp. You could use winscp. There is a command called winscp which you can download, and you can copy this to our server. So I'm saying student at Hadoop 1. I'm copying this file which we just exported, and I'm copying it to the server into my folder called as Giri. Alright, let me also parallelly log in. Alright. Now here you can see, is the font visible in the terminal? So let me just go to my folder. Now here the file must have come by now, called sg word count. You can see that. If you have to execute this jar, what we need to do is Hadoop jar, and we say sg word count, and now we provide our driver class name. Our driver class name was, you can keep any driver you want. Our driver name is package name dot class name sg dot this. Now let's see what happens. All right. So it says that, so if there's no executable permission, you can say chmod plus x, but you don't need to execute it. Hadoop will execute it for you. Okay. You try this command. What does it say? All right. Now this command has run. It's just saying that you have to provide input directory and output directory. And remember, this input directory, this output is being printed by our program. Do you see this? If argument length is less than 2, meaning people have not provided the argument, print this out and then exit. Okay. And if the people have provided argument, then pass that to the job here. Okay, so let's try to pass that. And also note, all of this, it is going to be from HDFS, not from local file system, HDFS. Okay, so there is a folder called word count, and we say input, and we also say sg word count, and we say output, output 21 fab. So it says the output 21 fab already exists. Let me put J with it and then see. Alright, did I make any more mistakes? So it has started running my MapReduce job. And same way, you can also run it. Let's see the health of our systems. I've not checked the health for a couple of days now. Alright, so except for secondary name node, everything is running fine. Yarn is also fine. Alright, so it has written, and always take care of these parts. It says that there is only one map task, but there were two reduced tasks. And who said it's two? Because we said job.set num reduced task is two. Okay, so there are two reduced tasks and one map tasks. Okay, so keep these things in mind. We'll show a little bit more details later on. Okay, and yeah, now let's have a look at it. What we have written to the, so, Hadoop fs minus ls. Okay, you can see that there are two parts here and there, and let's see. Okay, so you can see that the output has been generated. Sounds good to you? The word counts have been generated. Now imagine this, you were supposed to do some more stuff in your Java code. There is a legacy library, or there is a emailing you want to do from inside map, or you want to connect to a database, which means you will require a driver and all of that. So that all is possible. All you need to do is put the jar, put the library into first your class path of Eclipse, so that your code can compile. Once your code has compiled, then you cop along with your code, copy the libraries to the server, and there, while running Hadoop jar, specify specify an argument called uselibs. And using uselibs, you can pass a list of comma separated libraries in which your functions are there, in which the classes are there which are using in your code. Okay, sounds good to you? All right. Also, whenever you are writing a code, it's a good practice to first write the test case and then write the code. Okay. Do so. The way you write test cases is you create a class, called stub test, and the testing is done using MapReduce, sorry, MR unit. Here, you will see that there are very interesting classes in this, which basically emulate or fake, which basically fake the whole MapReduce process. So there is something called map driver, which is provided by this MR unit. You can see the map driver is provided by MR unit. Similarly, there is a reduce driver, there is a map reduce driver, and as we discussed, we will be testing our map, our reduce, and our map reduce separately. Okay, so here you can see that although I have not done it, you guys should do it. I have not tested my mapper separately. Okay. Here I'm testing both the things together. I created my MapReduce driver. Okay, and this driver knows which classes am I going to execute. You can see this. So I'm telling this driver. So now my driver is not going to get used. This driver is going to get used. And in this driver, I'm telling it that this is my mapper, this is my reducer, and please execute it by saying MapReduce driver dot run, and whatever output I get, I just iterate over this output, compare the results, and be happy. Okay, and we all to MapReduce driver, I'm also providing that this is my input file or the input content. This is the input content. Sounds good to you? Here, so this MapReduce function will basically test it. All right. So go through this code, understand how does the MapReduce look in Java, and the same project is available inside the LMS. Okay, and that's all. So locally, I'll show you how to run it locally. Here, just uh, go to this site and right click on your file and say run as JUnit test case. Okay, you say proceed. You can see it has generated the output very quickly, locally itself. This is the output of the word count program. Okay, so we did not need to upload this and wait for MapReduce to finish, and also we did not overloaded our cluster. So we were able to do everything from inside of Eclipse. All right. So if we don't like something, we just change it and run it again. We can say, from here, run it again. All right, and then it'll keep running. So you can see on the window that it has printed. Ideally, you should be writing things like assert true, assert true, assert equals. So to compare the actual value with this, and every time you write assert, that is counted as a test case. All right. So we will discuss something. So this is okay, right, for you? Any questions still here? Have you guys gone to sleep or something? Are you there? All right. So any questions here? Okay. So go through this code, try to write your own test cases, experiment with it. If you have any questions, drop me an email immediately or give me a call on my number if you have any doubt. All right? Okay. And nevertheless, if you do not want to do this, don't want to use your Python and use streaming. For most of the cases, streaming is sufficient. Okay. So which language, with any programming language, you are okay with, Santosh? SQL. Okay. Okay. So why don't you just go through the video which is there? Just first, I think first 3 hours would be sufficient. First 2 plus 2, 4 hours will be sufficient for you. Okay. Hardly. Within first 4 hours, you'll be up and running. Okay. Okay. Are you saturated, or should I describe the input splits and start continue? All right. Yeah. So yeah, the only thing I want to leave you with this example, basically we always talked about blocks when we talked about HDFS. Now you see the block boundary. Imagine that your file has 5 lines, and then these are lines. So there are 11 lines in your file. Fifth line is being cut at the boundary. Similarly, ninth line is being cut at the boundary. And to avoid this, Hadoop creates something called input splits. And this split is something you can customize. Okay, so a little bit of a behavioral tuning is done on input split. The boundary block, which is sliced into two, it gets transferred from the second node to the first node so that the input split can be properly prepared. Okay, we will talk about input splits tomorrow. All right, we'll talk about this tomorrow again, and we'll go into the details on how can you customize it. All right, great. Thank you very much. It was a great session. All right, see you tomorrow. Bye bye.